And there we go. Okay, today we're going to continue on with a few more examples of what we've been doing. Okay, working on applications of the quadratic formula. Okay, the ones we've been working on so far have been pretty straightforward. Okay, word problems surrounding easily known or very familiar geometric shapes. Okay, descriptions of things going on with rectangles and triangles and circles and stuff like that. Okay, and that's what I think you can probably expect from the majority of the problems that might come your way from an application of a quadratic type of a question. Okay, formulas or shapes that we have formulas that go with. So they can ask us a little bit deeper of an algebra 1 question without really making it too difficult. Okay. What we're going to see today is a different type of or different variety of questions that they may ask you, and these are going to border along a completely different mindset. These, instead of giving you the little paragraph description that we've been seeing the last couple of days, and then you have to write the equation out of the description, and then get it into quadratic form and get it in the calculator and solve it. What you're going to see is they are possibly going to bring more advanced mathematics or possibly even physics type of formulas to the table, and then ask you to work with them. Okay, there's a couple of formulas that are on the screen right now, and we'll read over this here in a second. And unfortunately, what will happen is if a question were to show up on end of course or tax, whatever, that goes along these type of lines. Unfortunately, what a lot of people are going to do is they're going to read the question and then immediately decide that it is too hard, it sounds too difficult, they're going to just guess at it, and they're going to move on to the next question. Okay, so I'm going to renew a request that I've made of us several times this year. Do not get freaked out by problems that sound difficult. Do not throw in the towel on questions that look difficult. Many times, the ones that take the most words to describe or the most complicated looking formula that's provided, a lot of times those are the easiest questions on the test. Okay, I'm not scared of the ones where they fill up an entire paper with a paragraph and a complicated diagram or complicated formula. I'm not scared of those at all. I'm scared of the ones that do exactly the opposite. They don't give us very much information at all. Very small type of a problem. Those are the ones that concern me, because the less information they give us, the more things they can ask us. If they're going to take the time to give us a bunch of stuff, there's very little that they can ask us, usually in those instances. And you're going to see that to be true here today. Okay, here's this problem, or this isn't a problem, this is just a setup. This is an actual formula from the world of physics, which is a class that most of us are going to have to endure these days with physics and algebra 2, of course, being the requirements for the recommended diploma program. Okay, for an object thrown into the air with an initial upward velocity of v naught. Now, I'm not sure if you have come across this in your travels through IPC. Okay, that little zero, okay, that's called a subscript. I hope we know that when you write a letter that's kind of written down lower and small. Kind of, we deal with superscripts all the time. Okay, exponents. Okay, those are superscripts. When it's written down at the bottom, it's called a subscript, and they use them in physics calculations quite a bit. And it looks like it says zero, v0. Okay, but it's actually called naught, and naught is the value that they use at the very beginning of a problem. Okay, so like when they set up a problem, and the split second that it is either beginning or about to begin, that is naught. Okay, that is the beginning point of the formula, of the problem. So for an object thrown into the air with an initial upward velocity of v naught and an initial height of h naught, the height naught, okay, wherever the height is of the problem right as it's beginning, then its distance from the surface is found by the following formulas. D equals -5 times time squared plus v naught times time plus h naught, where t represents the seconds in the air and d represents the distance in meters from the ground. As I said, I'm very fearful that a lot of people are going to go, whoa, 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 that's way too hard. I'm going to just guess at it. I'm going to skip it. I'm going to move on. And that is a terrible strategy. Okay, you're going to see these problems aren't that difficult. Now, we have another formula that's down here, and I'll tell you the only difference between the two formulas is one of them is representing distance in meters from the ground. The other one is representing distance in feet from the ground. And if you look into the two formulas, you'll see that they are nearly identical with one exception. The coefficient of t squared has changed. Now, of course, one of them is represented in meters, one of them is represented in feet. Are we basically familiar with the difference between a meter and a foot? Okay, I think some people might, and I think some people might not. Let me grab a meter stick and a yardstick here. Okay, let's just start off with the simple and the obvious. Okay, a foot. How many inches are there in a foot? 12 inches in a foot. Hopefully everybody knows that. Okay, how many inches are there in a meter? Does anybody know? Um, It's not a direct translation because feet is the standard measurement system that is typically only used in the United States. Meters is the metric measuring system, which is used in the majority of the rest of the world. Okay, this is a yardstick. Okay, how many inches are there in a yard? There are 36. Exactly. There are 3 feet in a yard, 12 inches in each foot. This is a meter stick. Okay. There's no direct translation, but the rough translation is there are approximately 39.4 inches in a meter. Okay, so it runs about, a meter is about 3.5 inches longer than a yard. Okay, just so you know. Okay, and that's the reason for the difference in these coefficients. Now, you won't be expected to have those formulas memorized or anything like that. If they are going to bring up a problem like this on an Algebra 1 test, they will provide these formulas for you. When it comes down to a physics test, these are the kind of formulas that'll be on your formula chart. Okay. But anyway, it's not really about the formula. It's about the type of problems that they may associate with formulas that are like this. Okay? A lot of people are going to look at these formulas and, like I said, we're going to freak out. Don't freak out. As a matter of fact, be grateful. The more complicated the formula looks, probably the chances are the less they're going to be able to ask you about the formula. Okay? Formulas come with variables. Variables represent numbers. All we're going to have to do is get the numbers out of the problem, plug them in for the variables in the formula, and whichever variable is left over, we solve for it. That's what we do. That's what Algebra 1 is about. Taking an equation, whichever variable is left, solve for it. Get its value. That's your answer. Okay, so let's take a look at a problem that deals with these formulas. I copied and pasted the formulas up there at the right-hand side. Now, this problem says a football is kicked into the air with an initial upward velocity of 25 meters per second. Okay, and that is the way, you should remember this from your days in IPC, velocity is measured, an amount of distance over an amount of time. Okay, 25 meters per second. That's pretty a standard measurement, meters per second. And assume the initial height was ground level, and then we're asked a series of questions. Calculate its height after 2 seconds, after 3 seconds. When will the ball be 20 meters above the ground? Sketch a graph representing the function. What is an acceptable window? When will the ball hit the ground? What will be the greatest height reached by the football? At what time will this occur? What part of the graph represents this situation? There's roughly 10 questions sitting on this page right now, and it's all based upon one formula. If there is anything scary about these problems, that is it. They can give us one formula and they can ask us a wide variety of things about it. Okay, but there's a very limited amount of numerical information that they can ask us about. It's just up to us to apply those numbers to the problem that they're talking about. You're going to see it's really not that difficult. Okay, well, let's take a look at the formulas for just a second. Okay, we're probably already eyeballing the formulas going, man alive, those things look really complicated. I don't know how I'm going to be able to do this. Okay, well, let's look. There are variables in the formulas. Like we said, variables represent numbers, and we're going to plug numbers in for those variables. What variables are there? There is D. What else is there? There's time. Okay, so we've got distance and time. We have initial velocity, V naught. Okay, and we have initial height, h naught. Each of those formulas carries 4 different variables in it. Okay, so how many pieces of information are we going to have to be able to plug in so that we can solve for anything in one of these formulas? Okay, 4 variables. How many pieces are you going to have to be able to plug in? Got to be able to plug in 3 of them, right? Because if we can get an equation down to 1 variable, then we can solve for the variable and life is good. So we're going to have 3 values provided for us either by the problem or by the question, and whatever the one remaining piece of information is, that's what we're solving for. Okay, so let's take a look at the problem again and see what they did provide. A football is kicked into the air with an initial upward velocity of 25 meters per second squared. What did they just give us? They gave us initial velocity, v naught. Okay, there went one of the variables. What else did they provide us? Assume the initial height was ground level. What did they just say there? Okay, they gave us h naught. What's its value? Ground level, 0. Okay, there went another one of the variables. Okay, so we're down to 2 variables. We've got h naught taken care of. We've got v naught taken care of. The only thing we can do now is we can consider distance or time. And let's look at the question. Calculate the height after 2 seconds. There went time. Okay, based upon the problem that was given to us and the question that was asked, the only thing that we can find at this point is the distance that the football has traveled. Okay, so let's see what we have here. We're obviously looking for distance. Okay, so plugging into the formula they gave us. Which one of the formulas do we want to use? Want to use meters or feet? Okay, problem was talking in meters, so we're going to use the formula that deals with meters. Okay, distance equals -5, and the formula says to take that -5 and multiply it by time squared. Okay, well, do we know a time? Yeah, that's what the question is asking about. We have 2 seconds that have elapsed into this problem. So time squared plus the initial velocity. Initial velocity. Well, the problem identified initial velocity as 25. Okay, and the formula says to take that initial velocity and multiply it once again times time, which is still 2 seconds because we're still working on this problem. And then add to that the initial height, which in this case is nothing. Okay. Now the initial height can change. Okay, so a lot of the problems you're going to deal with on problems like this, it'll be starting at ground level. Okay, but some of them may be the person standing on top of a rooftop that's 15 feet off the ground, or the person's on a cliff, or the person's down in a hole, in which case the initial height is going to move up and down according to where ground level is at. Okay, well, the only thing we can solve for, as we said, is distance. The rest of this is all just numbers. There's really nothing to it except figuring out what number that all is. Okay, and I know in most cases that would mean going to our calculator and saying, okay, calculator, I need a little help with this. I need to know what -5 times 2 squared plus 25 times 2 plus 0 is. And you don't have to put the plus 0 on there because it doesn't actually change anything, but you can put it in there if it makes you feel better. And the only thing that we could solve is distance, so that's what this number represents. The problem wants to know, calculate the height after 2 seconds. The distance is 30 meters. Okay, really nothing to it. Plug in numbers into a formula. Question turns around and says, okay, what happens after 3 seconds? Well, what does that change? All it changes is instead of 2 seconds, we're looking at 3 seconds. Okay, so we're just going to replace these numbers. And if you're not familiar with it, if you hit second, enter, okay, it's where it says entry on your calculator, it will bring back the previous equation that you've typed up, and you can go back and edit it. Okay, very handy if you have to do the same equation over and over again, or perhaps if you typo something and you just want to go back and correct your typo, hit second entry, and then you can go back into the equation and change what you want. So all I've done is just changed all of the 2 seconds to 3 seconds in this case. Uh-oh, what happened there? It gave us the same, okay, distance. We're going to stop right there momentarily and we're going to talk about something. Was anybody surprised by the answer that we got on A1, where it said 30 meters? Did that come out strange to anybody in your mind? Okay. What was strange about it? Anybody? Anybody have a thought why that might not kind of make common sense? What did the problem establish? How fast or how far was the ball going at the beginning of the problem? 25 meters per second. But then the question turns around and asks, how far has the ball traveled after 2 seconds? Well, wouldn't common sense try to tell you that it's 25 meters for 1 second and 25 meters for the second, so it should be 50 meters for 2 seconds worth of travel? Common sense wise, that would seem reasonable. And I would be willing to bet that that will be one of the answer choices on the test if this is a test question, that they would put 50 meters on there. Okay. Well, the formula we gave us didn't suggest 50 meters. It told us it was going to be 30 meters. Why? Why the difference? How come it wasn't 50 meters? If it's 25 meters per second and 2 seconds go by, why didn't the ball travel 50 meters? Because we're not multiplying. Okay, yeah, we're following a formula instead. Okay. Um, let's think about the situation, the scenario they've got going on here. Okay. Person kicks the ball straight up. What starts to happen to the ball immediately after it's kicked? Starting to slow down. Why is it slowing down? Gravity's got it. Okay, gravity's got it. Okay, so to put this into physics terms, what happens when you kick the ball straight up in the air, you have applied a force to the ball. Okay, that force tries to take the ball infinitely 25 meters per second. It wants to go 25 meters per second forever. Okay, so that force has been applied, the ball is taking off, but immediately gravity begins working against it. Okay, because gravity is constantly working against stuff. Okay, so it's heading up at 25 meters per second, but immediately gravity starts to slow it down. Okay, so after 2 seconds, instead of getting all the way up to 50 meters, it only gets up to 30 meters. Now, what is the deal with A2 up there? How come we're at 30 meters at 2 seconds and 30 meters after 3 seconds? What's happening there? Yeah, there's a couple of possible explanations here. Okay, one of them would be, well, maybe at 2 seconds it's still on its way up, but somewhere in between 2 seconds and 3 seconds it has returned and now it's back on its way down and you're back at 30 meters again after 3 seconds. That's a possibility. Okay, but also let's think about what happens on the path of this ball when it's going upward, when it reaches its peak. Okay, does it go straight up, get there, and just kind of immediately turn back around and come back down like it bounces off of a ceiling? No, what happens to it? Slows down, slows down, slows down, slows down until it reaches its peak. And it almost seems to hang there for just a moment, right? I mean, we've all seen balls float in the air. Okay, it's kind of what they do. It almost seems like for a moment there, it's devoid of gravity. It doesn't seem to obey the laws of gravity. And it is. It's just one of those that's so far up there, our eyes can't really see how little it's traveling. So it's very possible that at 2 seconds, it may be almost up, and then you've got that little bit of hang time is that from 2 seconds to 3 seconds. So it's very possible we might be right at the peak of the path of this ball, and that's why those two measurements between 2 seconds and 3 seconds both came out the same. Okay, good. So it seems like y'all had a little bit of an idea of what that one was maybe trying to do. B says, when will it be 20 meters off of the ground? Well, once again, we can only solve for one variable. And it really doesn't matter which variable it is. We will plug in what we have, we will plug in what they're asking, and we will see what we are left over with. Okay, well, using the formula, this time they provided us with 20 meters. They gave us distance this time, and the question is when, which is time. Okay, so plugging into the formula, this time we've got a distance of 20 which equals -5 times time squared, but we don't know what time is. And that's going to be added to the initial velocity, which is still 25, multiplied by time, we don't know what time is, and then added to the initial height, which is still 0. Okay. Well, folks, looking at that, that ought to look real familiar. Okay, that is very close to a quadratic equation. Okay, so just like we've been doing for the last couple of weeks now, we are almost in a position where we could take this to the calculator, we could program it in, we could find out what's going on. What's the one thing you need to do with this equation before we're able to go to the calculator and find a solution? Exactly. Move everything to one side, okay, of the equal sign. We need everything isolated, okay? And probably the easiest thing to do would be to move the positive 20 over to the right since everything else is already over there. Okay, so to move the positive 20, we would subtract it to the other side. That would leave you with 0 equals 5t squared plus 25t, and then minus 20. Oops. 25t minus 20. Okay, once everything's on one side of the equal side, we should be pretty much home free. We've been working problems like this for quite a while now. Okay, we've got 5 times the variable squared plus 25 times the variable minus 20. Okay, just typing it straight up, hit zoom standard. Oops, I forgot to copy my equation correctly. It wasn't 5x squared, it was negative 5x squared. Let's have a look at it now. That looks a little better. Okay. Question is what? When will it be 20 meters off of the ground? Okay. Well, we've got the equation typed in. We have two possibilities. Okay, two possibilities. Why two different possibilities for when it's 20 minutes off or 20 meters off the ground? Yeah, 20 meters off the ground, passing 20 meters on the way up, and then 20 meters off the ground, passing 20 meters on the way down. Okay, so two time instances, and I think it's pretty clear to see from that graph that time is either going to equal 1 second, 2, 3, or time is going to equal 4 seconds. And you can, of course, use the calculate 0 function to find those values out if you need them. Okay, but it seems pretty clear that seconds are going to equal either +1 or +4. Now, here's a little bit of an opportunity here to talk to you about something I've been meaning to mention for a while. Sketch a graph representing the function. What is an acceptable window? Now, let me talk to you about what it means when it says sketch. Okay. Unfortunately, some of you have confused the word sketch with kind of like drawing when you're in kindergarten. Yeah, it's basically a doodle. That's a perfect way of putting it. Sketch a graph representing the function. Unfortunately, a lot of people are going, okay, well, let me get the function, and the entire function would be, what is it, -5x squared plus the initial velocity, which is 25 times the variable, and then plus the initial height. Okay, so here comes the entire function. Okay, and what a lot of people have been doing is going, okay, what's sketch the function? People go, wee, and we just kind of throw a parabola onto a piece of paper with absolutely nothing marked or nothing labeled or no axes or anything like that. That is not a sketch. Yeah, that is a doodle right there. That is just something that we went, all right, it kind of goes like that in the calculator, so I kind of went like that on the paper. That's useless. Okay, the only piece of information that can be told about that graph is it is upside down. We can't tell how wide it is. We can't tell how narrow it is. We can't tell if it's moved up, vertically shifted up or down. We can't tell if it's moved left or right in the graph. That is a useless graph. So what we really need to be able to do is we need to, as far as a sketch is concerned, a sketch does not mean oh, it doesn't really matter what the picture looks like. A sketch means, hey, you don't have to have it perfect as far as hitting every single point that it's need to go through as it goes through it. But you do need to have the basic ideas. Where does it cross the x-axis at? Does it cross it once or twice? Where are those values? How high up does the graph actually get to? How far down does the graph actually get to? Those kind of things need to be able to be told in a quote-unquote sketch. Okay, if we said draw an accurate graph, well, you better hit every point that thing's supposed to hit or your graph is going to be wrong. If you ask for a sketch, it better have the basic landmarks. If it hits an axis, where does it hit that axis at? If it peaks and turns and goes the other direction, then fine. Where does that happen at? Or if it troughs, where does that happen at? Okay. Well, and not having being an artist, we're in algebra class. We need to be mathematicians about this. Obviously, our graph passes through the origin, so that needs to be a point that is marked on your graph. Our graph crosses the x-axis again at +5, so that needs to happen on your graph also. Okay. Well, this is both sides of the graph. Okay, one thing we might need to know is how high up. Okay, it seems pretty clear our parabola is peaking up top there somewhere. So let's have a look at kind of what it's doing there. Okay, we got a peak. We can zoom in on it a little bit. Makes you feel better. Okay, so I'm going to move my cursor up near the top. And there's the peak of the graph. Okay, now we'd really like to know where this peak is so we can mark it on the y-axis and get an idea of how far up there that is. Okay, there's a couple of different ways you can go about this. The least accurate way is unfortunately the way that everybody's in love with. We think trace answers everything, and it doesn't. Okay, but we can use the trace function to get a basic idea of where the peak might be. The problem with trace is it steps at its own intervals, not your intervals. So you may not be able to get the value that's at the peak. Okay, so we've got this 31.235853, but that doesn't really tell us, I mean, it's close, but what is the actual value? Now I'm going to show you something else here that you may or may not be aware of, also in the calculate menu. Okay, I know I haven't mentioned it this year, and I don't know if you've had another teacher that has, but option number 3 and option number 4 there, they say minimum and maximum. Okay, what that means is minimum is how far down does a graph go. Okay, so if you're looking at a parabola that has a bottom to it, okay, using the minimum function, we can find out how far down that bottom is. Or number 4, maximum, if the parabola is upside down, we can find out how tall or how high up that peak is. Okay, and that's what we have going on here. We're going to ask for a maximum, option number 4, and then it's going to ask you for the same type of questions that it would ask you for if you were calculating a 0. How far to the left do you want to look in the graph? How far to the right do you want to look in the graph? And then do you want to solve it? So left bound, come to the left of the peak a little bit, press enter. Okay, go back to the right a little bit, press enter, and then you can just hit enter for guess, and it will tell you precisely the coordinate of the highest point of the graph. And it'll do the same thing for minimum if the graph is going the other direction. Okay. So there we go. No, the other one said 31.238, blah, blah, blah. It wasn't 0.238, it was 1/4. Okay, it was 31 and a fourth. Okay, well, that is 25. No, the other one, I got you. Okay, so in that case, we would be able to go, okay, I've got, 10, 20, 30, and we would be able to put a peak out here at 2.5, 31.5, and then when we go to sketch our graph, we've got the pertinent landmarks. We can really tell how our parabola fits into the graph. That's a sketch. Okay, that is a sketch. All right. Now the problem also asks for an acceptable window. Okay, acceptable window. This is a typical concern, typical type problem I'm worried about for taxer, of course. Okay, this is very similar. Okay, asking about an acceptable window is the same thing as asking about a reasonable domain or a reasonable range. Okay, parabolas continue infinitely, but the problems that they are related to do not continue infinitely. We've seen a little bit of that over the last 2 days. We've seen graphs that have crossed the x-axis 2 times, but one of those intersections was impossible because we had a situation where a negative value wasn't a realistic situation. Okay, so when it comes down to thinking about an acceptable window or a reasonable domain or a reasonable range, what we need to do is we need to think about the scenario that we're working on and decide how much do we actually need to be considering here. Okay, well, let's think about this scenario we've got going on here, the kicking the football. Okay, the person kicks the football takes off, it goes up there, it peaks, it comes back down, okay, blah, blah, blah. Okay, do we need this entire parabola to describe what this football can do? Okay, if you're saying no, what would possibly be something that would be unneeded from this graph? What about it? On the ground? Well, okay, on the ground is possible, right? I mean, if the ball is starting on the ground, it's going to go up, it's going to come back down, it's going to hit the ground again. So on the ground is a possibility. What's not a possibility? Yeah, okay, it's not, I mean, it's going to go up, it's going to peak, it's going to come back down. Did the ball come from underground? Did the ball come from negative time? Okay, so after this graph gets below the x-axis on the left side, this is impossible. Okay, there's nothing before the initial time. There's nothing before the initial velocity. There's nothing before the initial height. That's why it's initial. That's what those knots are for. That is the beginning of this experiment, and nothing happens before that. So in all reality, when that graph hits the x-axis on the left side, we don't need the parabola anymore outside of that. Okay, is there anything else about the parabola you might not need? What about this tail? Okay, unless that ball's attached with a drill on it, okay, when the ball's kicked up, it's going to go up, it's going to come back down, it's going to hit the ground. It is not going to go underground. Okay, so that part of the graph is not needed either. It's not an acceptable possibility for this particular situation. So when it says what is an acceptable window, well, this is what the ball can do. So the window only needs to reflect what the ball can do. So what we really need to do is kind of establish what domain can do, what range can do, and the domain can exist anywhere in between 0 seconds, which would be the beginning of the experiment, and 5 seconds, which when the ball hits the ground, that's the end of the experiment. So 0 to 5. X can be less than or equal to 0, or it can be, X is going to be greater than or equal to 0, and it's going to be less than or equal to 5. Okay, what can the range do? Okay, well, once again, okay, the Y value, the height, it can be 0, okay, and it can get all the way up to, what was it we said, 31 and a quarter. Okay, so as Joe Abel said, 32 is a reasonable number, okay, to shut the graph off at. Okay. So if you were actually programming your calculator, went into the window set, okay, that those values would get you a perfect representation of what this experiment can do. Okay, so that's an acceptable window by looking at the domain and range and saying really what x's do I really need to look at, what y's do I really need to look at. When will the ball hit the ground? Okay, I think pretty clearly from the graph that we've already established here and the window that we've got going, the acceptable window, I think it's pretty clear that it's going to be 5 seconds. But once again, to do the calculation, when will the ball hit the ground? Okay, well, that's basically a matter of looking at the graph, looking at those intersections with the x-axis. Okay, it's obviously going to be at the ground at 0 seconds at the beginning of the experiment. It's going to be at the ground at 5 seconds. But I think the use of the word hit, when will the ball hit the ground? That's when it's coming back down. So I think that would be time equals 5 seconds. What will be the greatest height reached by the football? At what time will this occur? What part of the graph represents this situation? Well, we've already answered the bulk of these questions by looking at the maximum. Okay, we calculated how high up it was. That was the max. And what'll be the greatest height? The greatest height would be 31 and 1/4 meters. At what time will this occur? Well, once again, there was your independent value, your x, okay, 2.5 seconds. Okay, that would be at 2.5 seconds. What part of the graph represents this situation? This location right here has a name. Okay, we talked about it way back at the very beginning, but haven't really mentioned it since then. Anybody remember what that guy's called? Say it again. Yeah, we do. This is a line of symmetry, okay, meaning that the graph is doing the same thing on either side of it. But this part where the graph itself makes contact with the line of symmetry, that guy's got a name. Anybody remember it? I mean, we were talking about maximums and minimums, but that's kind of a description. Its name is the vertex. Okay, the vertex of the parabola. Okay, that is the vertex of the parabola is the place where the parabola makes contact with the line of symmetry. So it's basically the location where the graph stops doing one thing and kind of does the exact same thing on the other side. Okay, so there you go. Now, folks, there's really not much these problems can do to you. I mean, we've got a bunch of junk up there, but then again, we answered like 10 questions. Was any of those any of those 10 questions really particularly difficult? It's not that hard. Okay, do not let difficult looking problems scare you away. Okay, and all they can do, this is a different problem. A skeet is fired from ground level up into the air with an initial velocity of 96 feet per second. How high is the skeet after half a second, 1 second, 3 seconds? What happens, if the skeet's been in the air for 5 seconds? How high is it? If the skeet's 120 feet in the air when it's hit, what are the possible times that it was in the air? Aside from it being a skeet shooter versus a football punter or whatever, okay, what's different about this problem? Nothing except for, I could say, they switched measurement systems on us. Before they were in metric with the meters, now they're in standard with the feet. That would simply mean that we would select the formula that uses feet rather than meters. There's really no difference. And looking over these problems, there's no difference in the way that these problems are solved opposed to the last problems. You plug in the values that you do have, and you will end up with one value that is still left unknown. That's what you're going to be solving for. Okay. A rock is thrown upwards from a 50-meter tall cliff on the water's edge at initial velocity of 15 meters per second, blah, blah, blah. What's different about this situation? Okay. V naught equals 50. They didn't start from the ground this time. The guy's up in the air when they started this experiment. It doesn't do anything. It's just a different value that plugs into the formula. It doesn't change anything. As Alpine jumps off the end of a ski jump, he has an initial upward velocity of 13 meters per second. The height at the end of the ski jump is 60 meters. There again, initial height, not at the ground level, 60 feet up, 60 meters up. Okay. Um, Again, battleship shooting projectiles. Assume it's at ground level. Okay. That's all these problems can do. Do not get intimidated by a difficult looking problem. The harder the problem looks, the more words the problem takes to describe itself. Those are probably easier than some of the other problems that are real short. And unfortunately, that's exactly the opposite of the way our brain is programmed to do it. We see it, oh, it's a big paragraph, it must be tough. No, it's not. Stick with it, read it. Let's see if we can figure it out. One question is the difference between pass and fail. One question is the difference between commended or not. This may be the one question, and it may scare you away because it looks bad, too bad. Well, you got nothing else to do. Have a look at it. Okay. What's going to happen now is for the next couple of days, I'm going to quit standing up here and doing examples and talking about examples. I'm going to bring some examples for you to work. Um, I'm probably not going to be here on Friday. Okay, I've got some things I've got to get taken care of, and it's got to be during the week when I do it. Okay, so tomorrow I'm going to bring you some examples. Hopefully you'll work hard on the examples. You'll ask questions that need to be asked and try to figure out how these problems work. Now, as we saw, these things are very, very simple today. All you have to do is plug in. So the ones I'm going to bring you are probably more like the ones that we went over on Monday and Tuesday. Here is a word problem talking about a square and a rectangle or whatever, and you got to draw a picture and figure out the equation that goes with it, figure out how to combine the equations and get a solution. Okay, so stuff like that. So hopefully you'll come in, you'll ask good questions tomorrow, get a good grasp of how it's working. Then you'll have more class time on Friday with the substitute that is here. And whatever you're unable to finish either in class on Thursday and in class on Friday will become an assignment that'll be due on Monday. Okay. We're looking at a Unit 10 test before terribly long, probably be the middle part of next week. So we got another opportunity for you to either increase your situation on your unit or your fifth 6 weeks grade, or possibly injure it. Okay, but anyway, test coming here in about a week.